Hello, today we are going to present you guys the vehicle delay study with Damien, Austin, and Didi. We did collect our data on October 25th at 12:30 at South Marietta Parkway Southeast southbound, and the reason why we did that was to determine the current performance level of an existing signal, to measure the average vehicle delay per approach.
After obtaining our field data, we were able to calculate the total vehicle delay per second, the average delay per stop vehicle in seconds, the average delay per approach vehicles in seconds, the average control delay, which is seconds per vehicle, and lastly, the total percent of vehicles stopped. On the right, we have a table from the Highway Capacity Manual, which shows us level of service limits. Group 7 collected their data in the afternoon, while Group 9 collected their data during the evening. As you can see, evening time has a higher volume of vehicles based on the total delay, which is 19,530 vehicles per second and 11,895 vehicles per second. We're able to calculate the average delay as well, which is 39.13 and 85.66 for the evening group. If we go back to our table, we can also get the level of service. So our controlled approach delay is 43.6. We can see that 43.6 is in between 35.1 to 55. So it's level of service D. And same thing for group 9.5, which is 70.32. And if we go to the table, 70.32 is in between 55.1 to 80, which is level of service E.
Jumping into the discussion, we have our group numbers outlined in red boxes and the evening groups outlined in the blue box. Because the evening group took their information during the peak hour, they saw 1.65 times the amount of vehicle seconds of delay. And this is the total amount of delayed time for the 350 car interval. Also, on the average delay per stop vehicle, they saw 2.19 times the amount of average delay in seconds that we saw during the noon rush hour. This is the length of time a stop vehicle is delayed at the intersection. We also saw a large difference in the control approach delay. For the afternoon hour, we saw 43.6 seconds per vehicle, while the evening saw 70.32. This is a 1.61 times difference in average delay per vehicle. The control delay is important because it helps estimate the level of service at the intersection. This accounts for deceleration, stopped, and acceleration delay. The percent total volume delayed actually saw a decrease by 0.74 times. This means that the evening group had less cars delayed on average. Taking into account the control delay, a level of service of D could be chosen for the afternoon group, and a level of service E could be chosen for the evening group. One source of error that we noted was large gaps in the queue line. This would restrict right turn movements from being able to access their turning lane, and also extended the southbound through movement queue much further than it needed to go. In conclusion, we were able to get the current service level of the southbound through movement of the intersection with our group getting a level service at D and the evening group getting a level service at E. Both of these values were calculated using the average vehicle delay. Our group saw 43.6 seconds of delay, while the evening group saw 70.32 seconds of average delay. To combat the delay, we recommend implementing an automated intersection delay estimation system that tracks real-time delay. This can increase traffic cycle effectiveness by alternating cycle lengths based on projected delay. And that concludes our presentation.